Alright guys, welcome to our channel Code with Sunny, and in this video I will be talking about another problem, hard type problem of the LeetCode sliding window maximum. Index number is 239 and the problem is of hard type as I've already said. Okay, so let me give it a like over here because we are going to learn a new concept, that is how we can find out the maximum element or the minimum element in a sliding window of size k. The term sliding window, like the window is going to be like slide over the all the that is all the indices of the array such that the size of this window is always remains constant, and let's say it is equal to k. Okay, so before wasting our time in any of the other stuffs, let's discuss this problem first. We have been given an array of integers nums, and there is a sliding window of size k which is moving from the very left of the array to the very right of the array. You can see only the k numbers in this window, that is the size of the window will remain constant. And what is the term of the window? Don't get confused, I will explain this in the very detail and also the best solution of this problem. Each time the sliding window moves right by one position, return the maximum sliding window. And what is that maximum sliding window? Okay, so no need to worry about, I will explain. And here are some few examples, I will explain that also. And okay, let's look over the constraint whether it is going to help us or not. You can see nums dot length is 10 power 5, and there is a k that is also going to vary up to nums dot length, which is the size of the window that will remain constant. Okay, so we have to print the, okay, return the maximum sliding window for every window of size k. Okay, so let's take an example and understand this problem. Suppose we have been given some elements of the array like 1, 3, 2, 4 and 6 and 7. Okay, so these are the elements of the array, and let's say we have been given k equal to 3. Okay, so we need to find an array of your answers such that every window of size k is giving the maximum element present in that window. Okay, so let's say k equal to 3 starts from this one, that is starting from I equal to 0 if we consider 0 based indexing, and for I equal to 2. Okay, so this is the window of size exactly equal to k starting from the very left. Okay, what is the maximum element present in this window? You can see maximum element present in this window is 3. So I'm going to append 3 to our answer. Okay, so 3 is one of the answers. And what is my next sliding window? That is next window of size k equal to 3. So this element will be popped out, and this is my next window of size equal to 3. Size equal to exactly equal to k, because I have taken here k as a 3, so k can be any integer, any positive integer. So now the size window size is also exactly equal to k, but the window is varying from I equal to 1 up to I equal to 3. And what is the maximum element present in this window? 4. So I'm going to append 4 to my answer. Okay, so what is the next sliding window? Next sliding window is now 467, I think. No, it is not 467, it is 246. So what is the maximum element present in 246? Maximum element present in 246 is coming out to be 6. So append 6 to your answer. And what is the next sliding window? Next sliding window is coming out to be 467, right? So what is the maximum element present in this window? 7. So your answer array would be like 3, 4, 6, 7. That is, find all the substrings of length exactly equal to 3 of this array, and substrings should be distinct. That is, you can see the first substring of length 3 is 132, next substring of 324, next substring would be 246, and next would be 467. And find the maximum element present in every subarray of size k equal to 3, and get the maximum element and append it to your answer. Note that the sequence matters over here, like you must have to start from the leftmost position. Okay, so 346 is your answer. Okay, so this is like pretty much simple. You can do like brute force technique, but this is not optimal for a very large n. And what we have to do now, we have to use certain data structures. So I'm going to write a data structures. And what is that data structure? Let us understand that. Alright, so the data structure that we are going to use is Deque. And this is going to be like efficient way. And what is I'm going to write? Efficient. You can use a segment tree also, but I don't consider segment tree to be a good choice to solve this problem. So Deque is the way that I'm going to use. Okay. So what I'm going to do is let's suppose we have been taken an array. This is our reference array. We will solve this, understand this concept with the help of this array. And suppose here k is exactly equal to 2. I will take a small example to get a better visualization. Okay, so the DQ is going to help us in this particular way. Let's try to understand that. Suppose this is the DQ, and you are must aware about that, the property of the DQ, that we can pop out the elements, and from the both side, that is, this is the front and this is the back side of this DQ. Also, we can push the elements on the both side. Okay, now there is a standard methodology, that is, that is finding the sliding window maximum is going to be performed by the DQ, and front element always always gives maximum or minimum element. Suppose we need to find sliding window minimum, then we need to pop out the your answer for a particular window from the front. And if you find out the sliding window maximum, again you have to pop out the front element from this DQ. Okay, then what is the difference? Okay, the way of pushing in the back side. Okay, how we can perform that? Okay, so in case of sliding window minimum, let us try to understand that first. The elements are, that is, the elements that will be present in this DQ would be forming a certain pattern. And what is that pattern? That is, this DQ will always store the sliding window minimum of the, that is the window minimum for the current window, and the pattern that is going to be followed, like suppose it should be like 2 4 6 8. That is the, there are, let's suppose 10 elements, but it is containing 2 4 6 8, and always the front element is going to give us the minimum or the maximum if for the respective cases, like sliding window minimum or sliding window maximum. Like 2 is going to give us the sliding window minimum for a current window. Okay, so this is going to be a specific pattern. This element is always going to be minimum, and the next element, that is, this is the front and this is the back, and the next element is always going to be like the greater than this previous element, and so on. And what about sliding window maximum? For a particular state of the window, the elements should be like 7 5 4 3. This is the any state of the sliding window maximum. The front element will always give you the maximum element of that window, and the back element will always be giving, okay, we cannot say that because we are fixing something for the front element only. Okay, so front element, in this case, this is case for sliding window maximum, and this is case for the minimum. Front element will always give us the maximum or the minimum respectively. Okay, let us try to understand how the elements are going to be processed. Okay, so we have the elements like 1 3 2 4, and in the certain step, what I am going to do is, suppose I am going to deal with sliding maximum. So what I'm going to do is, suppose we take another example, that is like, suppose we have pushed 5. Suppose 5 comes over here, and suppose k is still unknown. We don't know what is the value of k now. Let us deal with the only element. Suppose 5 comes over here, then comes over 6, then comes over 7, and now another element that is coming over here, let's say 9. Okay, or again another element comes over here, let's say 11. Now another element when comes over here is 9 8, let's say 8. Now if 8 comes over here, that is still all the elements, let's say k is equal to, okay, let's say k is equal to 9. Okay, now 5 comes, already 5 already comes, 6 already comes, 7 already comes, 9 already comes, 11 already comes. Now comes the main element 8. You can see when 8 comes over here, this 11 is not useful, and this 9 is also not useful, right? So when okay, so I think I have missed something. I should have to deal with sliding minimum. Okay, for now. Okay, so when 5 comes over here, then 6 comes, then 7 comes, 9 comes, 11 comes, then comes over 8. When 8 comes, you can see this 11 is not useful because 11 is already greater than 8. So, so if we have to deal with the minimum element, finding the minimum element in a particular window, we have to pop out this 11 because this is not going to give us the minimum, because we have already found some another minimum element 8, which is like strictly less than 11. So this element should be popped out, and again 9 is greater than 8. This is not going to be useful. I am going to pop it out. So and now the correct position of 8 is like after 7. So I will push this 8 element right now over here. Okay, Now again you can see if some another element comes over here like 6. Now if 6 comes over here, you can see 8 is not useful because another minimum element that we have encountered is 6. So I will pop 8 out, and 7 is still greater than 6. I will pop it out again. Now what is the correct position of this 6? It is over here after this 6. So my current state of the DQ is like 566. And okay, so this is like sequence of the steps. Whenever you want to push some elements, you can see this element is like greater than or less than what is the relation between my current element, and that is the current element that we have encountered, and backside of the element that is present in the DQ. Now you can see, you can have to observe one thing, right? That is, what is the value of this element? This is 5. This is always going to be minimum. Okay, and suppose we have another found element called 2. What is the relation between 6 and 2? 6 is greater and we need to find out the minimum. So I will pop it out 6 because 2 is not the correct position over here. Again 6 is greater than 2. Again 5 is greater than 2. So I will pop it out 5 also. Now the queue becomes empty. What is the correct position of this 2? The only 2 will present over here. And if we have been asked what is the minimum element now? Minimum element now is 2. Okay, so let us generalize some case. What is that general case? Let us try to understand that. Okay, so whenever let us say we have some certain state of the queue, and whenever and you want to just push some elements. Okay, push a particular element, push a element. Okay, you want to push a element, and if you want to push an element, you need to check one condition. While not equal to q dot empty, that is q is not empty, and let's say you have to deal with sliding window maximum. And what is the since we are dealing with sliding window maximum, front element will contain the maximum and back element will contain we don't know, but the pattern would be like, let's say, 9 7 6 5 4. This is the sequence of pattern. The front element will always be containing the maximum. So while q is non-empty, and let's say we have encountered some extra and another element x, we need to find out the relation between this back element, now here it is 4, and this x. So I will check it out. Since we need to find the maximum element, I need to find out the correct position of x in this queue. So if while q is not empty and q dot back is still strictly less than my new element x, I need to just pop it out the backside of the elements, q dot pop back. Note that this is DQ. We can also pop it out from the front, but still we are dealing with maximum. I need to check it out from the back and find out the correct position of this X. That is, whenever the backside element of this Q is going to be like strictly less than this X, still we haven't find the correct position of this X, so I need to pop out the backside of this elements of this Q. Okay, note that Q should be non-empty. Okay, after doing that, after certain popping operations, you can see I have found the correct position of this element x. So I will push into the q dot push back x. Okay, so this is for the pushing one element. Okay, then what is the correct way of getting your answer? So getting your answer would be like it should be always like getting from the front element. So your answer would be like q dot front if you want to get some maximum or the minimum element. Okay, now comes the main thing, popping an element. Popping an element. And what is the way of popping an element? Suppose we have the elements like 1 2 3 4, and suppose k is equal to 2. Okay, so you need to, if you have considered these two elements, now comes the extra element, what is 132. And if 132 comes over here, you can see if k is equal to 2, I need to deal with only these two elements, so I need to pop out this element. Okay, if I need to pop out this one, okay, let us understand this sequentially. Okay, and if we have to deal with sequentially, and let's say we need to find the maximum sliding window maximum for every window of size equal to 2. Now okay, so when one comes over here, and if you look out the sequence of operations, that is pushing an element, it is like while q is non-empty and q dot back is less than x. Okay, so still you can see now I have only this okay, let me erase this first. Okay, so you can see my queue is now empty, and if 1 comes over here, I will push up this one, because while q is not empty and q dot back should be less than x, strictly less than x, since my q is empty, I will push directly 1. And when again 3 comes, now I'm dealing with this 3, you can see my q dot back, my q is like this one, something like this one. Okay, so I will make some q. Okay, this is my q, and there is only a single element 1. So while q dot back is less than 3, you can see 1 is strictly less than 3, so I need to pop out this one. So this one element should be popped out, and what is the correct position of this 3 is like in the front of the q. So my new q would becomes like this one, only element containing 3. It means that we have dealt with these two elements. Now comes another element 2. If my new element comes over like 2, what I have to do? I have to place this 2 to its correct position. Okay. So what is the correct position? While q is not empty and q dot back is strictly less than x, pop out the elements. You can see 3 is like greater than 2, so I do not need to pop out the elements. So what is the correct position of this 2? So 3 and 2. But you can see we have dealt with all these two elements, 1, 3 and 2. I need to pop out this 1. Okay, I need to pop out this one, but 1 is not present in the queue. Okay, so what about when 1 would be present in the queue? That is, you need to pop out that element. Yes, we need to pop out that element. Here 1 is not present. I will take another example where 1 would be present, not 1, any other element. You can see this is not present, but when some element is present and we need to pop out some element, you need to write some relation. If q is non-empty, that is not equal to q is empty, and the element that we need to remove, that is, let's say this is rm, exactly equal to q dot front, then I need to pop out q dot front. This is the main clue, q dot pop front. Note that this is Deque, I can pop it from any of the side. So let's take another example where we have to deal with this case. Like we have some elements 5, 3, 2, and here k is 2. Okay, so we can see when 5 comes over here, then again 3 comes. This is the correct position of this 3. Now when comes over 2, I need to deal with only these two elements. So what is the correct position of this 2? It is 2 over here. But you can see the size of q is like greater than what? Greater than k equal to 2. So I need to pop out one element. But what is the element that should be popped out? That is this 5, and the q, state of the q, contains the front element as the 5. So here comes the major role. I need to remove 5, so I need to check if q is non-empty. Yes, it is okay, and my element that should be popped out exactly equal to q dot front. So I need to pop out q dot pop front, that is, I need to perform the operation q dot pop front. So this 5 element should be popped out. So now my new state of the queue becomes 3, 2. Okay. So summarizing all the things, that is, only I need to mention few of the points. That is, while you are going to push an element, check this condition while q is non-empty and q dot back is less than x for sliding window maximum. In case of sliding window minimum, you need to write less than, not less than. You need to write the reverse of this, that is greater than x. Okay, and perform the popping operations, and finally push out the q dot pushback x, finding the correct position of this x in the queue. Okay, this is for pushing an element, and getting your answer is only q dot front for both the cases. And popping an element is like if q is non-empty and removing element is exactly matching with the front element, perform the q dot front operation, that is q dot pop front operation. Okay, so let's move on to the code. And the code is like very much simple. You need to find out the answers for every sliding window of size equal to k. So deque int q and vector int answer, and this is storing the answer. So I iterate up to like this: for int I equal to 0, nums dot size I plus plus, insertion of an element, and how the element is going to be inserted while q is non-empty and q dot back is less than nums of I. We need to find the exact correct position of this nums of I. So until we haven't find the correct position of this nums of I, pop back the elements from the queue, q dot pop back, and finally we have found the correct position. Push the my current element in the queue, and if I is going to be like greater than or equal to k, we need to remove one element, right? So because we have to maintain a window of size k, so if I is like greater than or equal to k, remove the I minus kth position element. So if q is non-empty and q dot front exactly matches with the nums of I minus k, because my q always stores the sliding window maximum, that is the front element of the q. So I will pop out, that is perform the operation q dot pop front. Also you need to get the answers, like if I is going to be like greater than k minus 1, we have found a window of exactly size equal to k. So I will push up the answers, that is push back my answers of answer is equal to q dot front, as we all know, and finally return the answers. So this will give you an AC code, I think. Yes, I have already submitted, I think. Yes, first I have get the wrong answer because a small mistake over this equal to sign. Okay, so if you have any doubts, do let me know in the comment section of the video. And this question is really interesting, so I will also recommend to do some practice problems like jump game 6, I think. Yes, it is 6. Jump game 6 LeetCode. There is also a video present in my channel. If you're getting doubts, you can also visit that. Okay. So if you have any doubts, do let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and to subscribe to our YouTube channel for latest updates. Thank you for watching this video.